Okay, welcome back to the NCG and T seminar. Our speaker is Andrea Sciandra from Unito, who is currently visiting us here in Prague. And he's going to talk about Drinfeld braces, post-Hopf algebras, and Rota Baxter operators. Please.
Okay. Thank you, Thomas, and thanks to the organizers for this opportunity. So as why it doesn't work? Okay. As also Davide said before, when we have a monoidal category, we can define algebras and coalgebras inside the monoidal category. If your monoidal category has a braiding, this just satisfies the hexagonal axiom, not needed to be bijective. You are able to define bialgebras and Hopf algebras in your category M. So standard Hopf algebras are exactly Hopf algebras in vector spaces. So just to recall the definition, is just the datum of an algebra, which is also a coalgebra, such that the coproduct and the counit are algebra morphism, or equivalently, the unit and the multiplication are coalgebra morphism. And in fact, you can see that the first one tells you that delta is multiplicative, where again, A1 and A2 just mean Zwiddler notation, so the coproduct over A, and delta is unitary. And here you have epsilon multiplicative and epsilon unitary. And you also have a morphism S, which is a linear map that is a convolution inverse of the identity, so just satisfy these two conditions here. An Hopf algebra is co-commutative if the coproduct, doing the coproduct of an element is the same to doing the coproduct and then the flip map. So on elements is this one. So x1 tensor x2 is equal to x2 tensor x1. And the main difference between an Hopf algebra, a standard Hopf algebra, and a Hopf monoid in a braided monoidal category is just the compatibility condition between delta and n. So the fact that delta is multiplicative means this. And you can see that we use the braiding of the category sigma, that in case of vector space is just given by the flip map. And that you can see here that we use the delta over A, delta over B, then the flip map in the middle, and then multiplication and multiplication. So we will use the definition of monoid in a braided monoidal category later. So as also Davide said before, we can define for a Hopf algebra, in fact, we can define also Drinfeld module for a bialgebra H, but we give the definition for Hopf algebra because this is what we use later. So a Drinfeld module over an Hopf algebra H is just a vector space with a left module structure, which we denote by this harpoon here, and a left H comodule structure, which we denote by this rho, and we use the Zwiddler notation, so we omit the summation symbol, which are compatible in the following sense. And this is the same compatibility that also Davide told you before. So the category of Drinfeld modules is braided with braided given by this. So for any pair of Drinfeld modules, you can define this. So you can see that you flip x and y as the order. You apply the coaction of x, and you have x minus 1, which is something in H, and and x0, which is something in X, and then you act with H over Y. So you use the coaction of X and the action of Y. Okay. So just to tell in this case, if we consider Hopf algebras in the category of Drinfeld module, clearly this compatibility changes because we use the braiding of Drinfeld module instead of the flip map. And the braiding is, in fact, exactly this one. Okay, now I can introduce the definition of Drinfeld brace that we give together. So a Drinfeld brace is just a datum given by an Hopf algebra structure, a standard Hopf algebra structure, H bullet, so with antipode T, and a second product dot on H and a morphism S from H to H, such that H dot is an Hopf algebra, but in the category of Drinfeld module over H bullet, where it is a Drinfeld module with this action here that you can see we define using dot and bullet and S, the antipode of the dot structure, and the adjoint coaction. So H dot is a Drinfeld module, and it is also an Hopf algebra in the category of Drinfeld modules over the bullet structure. And moreover, if we define this new right harpoon in this way, this pair of action must satisfy this condition here, that we will see also later. This is really important. Moreover, the two operations have to satisfy the off-brace compatibility condition. So this is the same that you can see in the definition of off-brace, the same of before. But we have, in fact, more conditions on this category. So a morphism of Drinfeld brace is just, again, a morphism of co-algebras. The co-algebra structure is just one, is this delta epsilon. And it is also a morphism of algebra with respect to both the algebra operation, so dot and bullet. So this is the category of Drinfeld braces, and you can see that if we ask that H is co-commutative, then the joint coaction becomes trivial. And then, if we come back here, if the coaction is trivial, then this is just the flip map. You see that x1 is just 1, so you act with 1, so it is just y, and this is the flip map. So if your Hopf algebra is co-commutative, the coaction is trivial, then the braiding is just the flip map, and so H dot is a standard Hopf algebra. So if you require that your H is co-commutative, then you recover exactly the definition of co-commutative of brace in the sense of Angiono, Galindo, and Vendramin. So a Hopf algebra whose coproduct is co-commutative and satisfies just the last compatibility condition, because you can see also that this is automatically satisfied. If H is co-commutative, you can change A1 with A2 and B1 with B2. But if we remove the co-commutativity assumption, we have two different Hopf algebra. We have an Hopf algebra in vector spaces and an Hopf algebra in Drinfeld module. Okay. Now we can also
clarify very briefly this point. So you're saying that this notion of Drinfeld brace is not more general than Hopf brace. It's just that those two notions intersect when the Hopf algebra has co-commutativity.
Yeah, exactly. Okay. Under the co-commutativity assumption, they are the same definition. So a co-commutative brace is a co-commutative Drinfeld brace. Okay. If you remove co-commutativity, they are different because we have an Hopf algebra, standard Hopf algebra, and the Hopf algebra in Drinfeld module.
Okay, clear.
But this is the proper notion to have a correspondence with match pair, as we will see. So we can define, in fact, a match pair on a Hopf algebra. So we start with an Hopf algebra H, and a match pair of action is just given by a pair of action, a left action and a right action of H over itself, such that with these two actions, H is a module co-algebra. So this just means that the coproduct and the co-unit are linear with respect to the left and right action. And these three axioms are satisfied. So the first one just tells you how an element acts on a product. And the second one, how the right action acts on a product. While the third one is exactly a braided commutativity condition, as we will see before. So the product of two elements is just given by this product here, where we use the left and the right action. And a morphism of match pair of action is just a morphism of the subjacent of algebras compatible with the actions in this way here. Now, if we just assume 1 and 2, and instead of 3, we consider exactly this condition that also appear in the definition of Drinfeld brace, we have the notion of match pair of algebras in the sense of Majid. And these conditions, so 1 and 2 plus this one, are exactly the condition that you need to define the so-called double cross product of algebra, which is just H tensor H as a vector space with product defined in this way. So where we deform, in a sense, the standard tensor product algebra structure using the left and the right action in this way, with unit just given by 1 tensor 1 and the standard tensor coproduct algebra structure. We can also define an antipode, but this is not important in this way. And 1, 2, and this condition here are the condition that you need to obtain that this is, in fact, an Hopf algebra with this structure here. So what we have is that, in fact, our condition is stronger in the sense that if we assume 1 and 2 plus this condition here, so match pair of actions, in fact, we always obtain this one. So match pair of action are always match pair of algebras in the sense of Majid. And precisely, match pair of action coincide with the class of match pair of algebras such that the product of H seen as a morphism from the double cross product of H with itself into H is a morphism of algebras. So are exactly these match pair of algebras, the ones who have this additional property. Okay, and we are able to prove that if we start with a match pair of action, then if we keep, in fact, the left action and we define the adjoint coaction, you can see that here we goes into H bullet, which has antipode T. Then this is a Jeter-Drinfeld module. Moreover, we can define also a new product dot and the new antipode S using what? Using our starting product bullet of H, the starting antipode T of H bullet, and their pun, and a new S using, in fact, the starting antipode and their pun. And this gives us algebras in the category of Jeter-Drinfeld modules over H bullet. And you can see that in this case, the braiding operator over H is given by this one. And again, if H is cocommutative, the coaction, in fact, the adjoint coaction is trivial, and this becomes the standard flip map, and we recover, in fact, the definition of standard of algebra, let's say. So we have this theorem. So when we start with the match pair of action, we are able to obtain an algebra in the category of Jeter-Drinfeld modules. And in fact, we obtain a Jeter-Drinfeld brace. So if we start with the match pair of action, with this new dot and this new S, this datum is a Jeter-Drinfeld brace. But we also have the other way around. So this is an ISO of category. So if we start with the Jeter-Drinfeld brace, which is a datum of this form, we just keep the second structure, which is the standard of algebra. And we are able to define now a match pair, a couple of actions, a left and right action, in this way, obtaining a match pair of action. Yeah. Sorry.
But you don't actually mean isomorphism.
This is an ISO of categories.
It's a genuine isomorphism.
It's an ISO of categories, exactly an ISO. Yeah.
Okay.
Yeah. It's an equivalence when you consider a one cocycle, but if you consider a match pair of action, is precisely an
actual isomorphism.
Yeah. And if you assume cocommutativity, then you recover the ISO clearly between match pair over cocommutative of algebras and cocommutative of braces. So you can see that in the paper of Anguiono, Galindo, and Vendramin, in fact, it is given this ISO between match pair of action and of braces, but under the assumption of cocommutativity. If you remove the cocommutativity assumption, match pair becomes isomorphic to not of brace, but to this Jeter-Drinfeld brace. So to answer also the question that also David left before. Moreover, match pair of actions produce solution of the quantum Baxter equation given by this, so using the left action and the right action. And in fact, you can see that defining this as a braiding, this is exactly the braided commutativity with respect to this braiding here. And this braiding is involutive if and only if your multiplication is braided commutative. And so this is in a recent paper of Lee. And this also generalized the result obtained by Anguiono, Galindo, and Vendramin. In fact, they define exactly the same braiding operator. And this is involutive if and only if the dot product is commutative. But in this case, the product is in a different category. We have the category of Jeter-Drinfeld module. Okay. Now, we have obtained that Jeter-Drinfeld braces and match pair of action are isomorphic as categories. Now I want to give another category which is isomorphic to both of these two. And we will see later why this is important, why this is useful in a sense. So we can define a Jeter-Drinfeld post-Hopf algebra as just as datum of an algebra which is also a coalgebra. So for the moment, H is just an algebra and a coalgebra, equipped with a morphism S, which is an antipode substantially, so it satisfies this condition. In fact, we don't need a braiding to define this. So it is an algebra, a coalgebra with a map S that satisfies this. Moreover, it is equipped with a morphism of coalgebras, this harpoon here, satisfying these two conditions. So the first one just tells you that the product is linear with respect to the harpoon. And the second one is a deformed associativity. So you can see that X acting over Y acting over Z is this product acting over Z. So it is not just the product of X and Y, but it is a deformed associativity condition. Moreover, we also ask that if we look at the harpoon as a morphism from H to the endomorphism of H, this is convolution invertible. So this means that, in fact, there exists a unique beta satisfies this condition. You can see that we use the delta of H, so x1, x2, then alpha and beta and alpha, and then the product of endomorphism, so just the composition. So the coproduct of your starting coalgebra, H, then alpha and beta in both the two orders, and then the product of your codomain, so just the composition. And this must be what? Must be the epsilon followed by the unit. So it is just given by the identity as the endomorphism with this scalar, epsilon of x. Moreover, epsilon is a morphism of algebras, while delta is unitary, but it is not commutative in the usual sense, but it satisfies this strange relation here, where alpha and beta appear. And then we will see why this. Moreover, if we define a new bullet in this way, and this is exactly this guy here, you see, this part here, and the new S using beta, and the starting S, and the new harpoon, which mimic the definition that we also see before, then we also need to require that the new S is anti-comultiplicative, and again, the same compatibility condition of before all. So this is strange, a bit strange definition, but we will see how all these conditions are needed. So moreover, a morphism of Drinfeld post-Hopf is just a morphism of algebras and coalgebras. In fact, our data here are algebras which are also coalgebras. So we can ask for a morphism to be a morphism of algebras and coalgebras compatible with the harpoon again. So what happens if we assume cocommutativity? If you assume cocommutativity, this equality is automatically satisfied. One can also easily see that this holds. In fact, in this case, S is commultiplicative, because in this case, commultiplicative and anti-commultiplicative are the same. Moreover, what happens that if we go back here, you see that if the starting algebra is cocommutative, we can change x4 with x3, and then we can use this compatibility condition, and so we obtain the standard multiplicativity condition. So under cocommutativity, this delta becomes a morphism of algebras. And so since we start with something which is an algebra and also a coalgebra, now epsilon and delta are morphism of algebra, so it is a bialgebra, and S is the antipode. So under the cocommutativity assumption, this is a standard of algebra, equipped with a morphism of coalgebra satisfying 1 and 2 with the convolution inverse. So in fact, this is the notion of post-Hopf algebra, cocommutative post-Hopf algebra. So just considering this first part, so an Hopf algebra with the morphism of coalgebra, this harpoon satisfying 1 and 2, such that this alpha has a convolution inverse. Nothing more. So under the cocommutativity assumption, we recover the notion of cocommutative post-Hopf algebra of Lischang and Tang. As we, for Hopf braces, under the cocommutativity, we obtain cocommutative post-Hopf, cocommutative Hopf brace. But now, if we remove, in fact, commutativity, these definitions are different because we don't start with the standard of algebra, but with something which is algebra, coalgebra, with a strange compatibility, let's say, for the delta.
Just a quick question for the previous definition that you gave. So this alpha and beta, I'm wondering if is it true that the beta is just alpha composition with the antipode? Because so alpha has to be an algebra morphism or just a linear map? What is alpha?
This alpha is just a linear map. This alpha.
Okay, because if it would be an
No,
algebra
yeah,
morphism,
sure.
then of course beta would be just
Sure,
alpha
sure,
composition S.
sure,
Okay.
sure.
But here,
No, you have to require this because it's just a linear map in this case. Okay, so under cocommutativity, our definition collapses on cocommutative post-Hopf. If we remove cocommutativity, they are different because our starting datum is not a Hopf algebra, but it's just an algebra and a coalgebra. But what we can do is, if we start with the Drinfeld post-Hopf, and we define the bullet and S as before, so the definition were these two, okay. This forms a proper Hopf algebra, which is called the subjacent Hopf algebra in analogy with the definition given by Li, Sheng, and Tang. In fact, the definition of bullet and S are the same. And the starting datum, so H with dot, delta epsilon, and S, is now an Hopf algebra, but in the category of Drinfeld module over the subjacent Hopf algebra. So we start with something which is just an algebra, a coalgebra with an antipode. We build a proper Hopf algebra, and we realize that our starting datum is an Hopf algebra in the category of Drinfeld module over H bullet. With action given by harpoon that you have when you have Drinfeld post-Hopf and adjoint coaction. And again, you can see that if you require cocommutativity, the adjoint coaction is trivial. So the braiding of Drinfeld modules is just given by the flip map. And so H dot is a standard of algebra. And this, in fact, coincide with the definition of cocommutative post-Hopf algebra given by Li, Sheng, and Tang. Okay, and now these categories are in fact isomorphic. So when you start with a Drinfeld post-Hopf and you define the subjacent Hopf algebra, so this H bullet and this new harpoon and this new antipode, this datum here is Drinfeld brace. In fact, you can see that the second structure is a standard of algebra. The first one is an Hopf algebra in the category of Drinfeld modules over the second one. While if you start with a Drinfeld brace, you just keep the first structure and you define an harpoon in this way here. And this forms a Drinfeld post-Hopf. In fact, you can define the beta using the antipode and the harpoon. So when you have a Drinfeld post-Hopf, you define the subjacent Hopf algebra, and this gives you a Drinfeld brace. If you start with the Drinfeld brace, you just keep the dot structure, and you define an harpoon in this way. You can prove that alpha has a convolution inverse given by this beta, and so this is a Drinfeld post-Hopf algebra. And in fact, this is, again, an iso-Hopf category that under cocommutativity reduces to an iso between cocommutative post-Hopf algebras and cocommutative Hopf braces. So in fact, we have that these three categories are isomorphic, match pair of actions on a Hopf algebra, Drinfeld braces, and Drinfeld post-Hopf. And in fact, when we reduce to cocommutativity, match pair of action are isomorphic to cocommutative Hopf braces, which are cocommutative Drinfeld braces are the same. And this is proved by Angiono, Galinde, Vendramin. And cocommutative Hopf braces are isomorphic to cocommutative post-Hopf algebras. And this is proved in the paper of Li, Sheng, and Tang. So just we lift this isomorphism of categories to a not cocommutative setting. Okay, while this post-Hopf setting is useful in a sense, or is important in some sense, because when we start with a Drinfeld post-Hopf or a post-Hopf, this is not important just because we take the primitive elements, which is something cocommutative, and under cocommutativity, the definition are the same. So start with the post-Hopf algebra, let's say, in the sense of Li, Sheng, and Tang. Consider the primitive elements or your Hopf algebra. This is a Lie algebra with commutator, and with the starting harpoon, this is a post-Lie algebra in the sense of Vallet. So a post-Lie algebra is just the datum of a Lie algebra G together with a linear map from G tensor G to G, such that these two conditions are satisfied. So let us analyze this. So first of all, if you define this part here as a new bracket, sorry, this in fact gives you a new Lie algebra structure on G called the subjacent Lie algebra. And then 1 and 2 just tells you that you have an action of the subjacent Lie algebra on G. In fact, you can see that the first one just tells you that if you fix the first entry, this is a derivation. And then with this other one, just tells you that you have an action of the subjacent Lie algebra on the starting Lie algebra. Now, if the bracket is trivial, so you just have a vector space with a linear map such that 2 is satisfied, just put this to 0. You recover the previously known notion of pre-Lie algebra due to Gestenhaber, if I remember well. So these post-Lie algebra are a generalization of this pre-Lie algebra where you don't require that the bracket is trivial. You can recover the notion of pre-Lie algebra just considering vector spaces. Yeah. A pre-Lie algebra is, you can read the notion of pre-Lie algebra here just considering trivial bracket. So it is just a vector space with a linear map from G tensor G into G. So now this is trivial satisfied, and you have just this, just considering this equals to 0. Yeah.
The algebra is the algebra, you obtain a post-Hopf algebra.
If you start with the post-Lie algebra, the enveloping algebra is the post-Hopf. Yeah. As in fact, when you start with the post-Hopf, you take primitive elements, you obtain a post-Lie. Yeah. Yeah. And now, this is just to motivate the definition of post-Hopf. So we now know that these 3 categories are isomorphic match pair of actions, Drinfeld braces, and Drinfeld post-Hopf. And now I want to give some examples coming from co-quasi-triangular Hopf algebras. So when you start with, just recall maybe the definition of co-quasi-triangular Hopf algebra is an Hopf algebra equipped with a convolution invertible morphism R from H tensor H into the base field, satisfying these 3 axioms. So in fact, one can read them in terms of bradings. The first one just tells you that your braiding is a morphism in your category, while 2 and 3 correspond to the hexagonal axiom. Moreover, if the convolution inverse of R is just given by R op, so tau followed by R, then this is called a co-triangular structure. And it is well known that co-quasi-triangular structure corresponds to braidings on the category of comodules. Precisely when you have an R, you can define a braiding in this way here. So where you use, in fact, the coaction of your comodules X and Y, and you use the R on the part which is in H. And co-triangular structure correspond to symmetric braidings, so to braidings which are involutive. Now, when you have, co-quasi-triangular structure correspond to braiding on category of comodules, but now when you have a co-quasi-triangular structure, you are also able to define a different braiding operator using R and R minus 1. So you can see that here you use R minus 1, the flip map in the middle, and then R. And this is exactly how to define from a co-quasi-triangular structure a braiding on bicomodules. So this is exactly the braiding of bicomodules seen as a braiding operator, so restricted to H. But now the fact is that this braiding operator is exactly of this form here. So obtained with match pair of actions, where the match pair of actions are just retrieved by composed with identity tensor epsilon and epsilon identity. So this is a braiding operator. Now, if you compose it with identity tensor epsilon, you obtain a left action. If you compose it with epsilon tensor identity, you obtain a right action. And this pair of actions is a match pair of actions in the previous sense. And so you can rewrite your braiding in this way. So this braiding operator is obtained using this match pair of actions. And we know that when we have a match pair of actions are isomorphic as categories to Drinfeld brace and to Drinfeld post-Hopf. So if we have a match pair of actions, we can build a Drinfeld brace and a Drinfeld post-Hopf. In fact, we have this theorem that if we start with the co-quasi-triangular Hopf algebra, Then we obtain a Jeter-Drinfeld brace by defining dot and S. I come back maybe to the definition. So dot and S are defined, okay, in this way here, when you have a match pair, okay? Dot and S. Now we just use the left action coming from the R. So the definition is this for the dot, this for the S, but we use this action here. And this is the structure for dot and for S. Moreover, we know that they are, when we have Jeter-Drinfeld brace, is the same as speaking of Jeter-Drinfeld post-Hopf. In fact, we are able to define also an harpoon, which is given by this, and alpha as this convolution inverse map. So starting with the quasi-triangular of algebra, we are able to obtain a Jeter-Drinfeld brace and a Jeter-Drinfeld post-Hopf structure. And one can see that, in fact, the H dot structure that you obtain, which is an Hopf algebra in the category of Jeter-Drinfeld modules over the H bullet, coincides exactly with the transmutation in the sense of Majid of the H bullet. So this new structure that you obtain, which is an Hopf algebra in Jeter-Drinfeld modules, is the transmutation of your starting Hopf algebra. Yeah.
Saying from an R matrix, you can get these two actions that then correspond to some matched pair. Can you do also the other way around, that if you have a matched pair, that you can somehow construct an R matrix to view your Hopf algebra that you have as a co-quasi-triangular?
This I don't know. Okay, a matched pair of action gives you a solution of the quantum Yang-Baxter. So you can do some FRT if you want.
Right.
But yeah, that's...
Then this would be some quotient. Maybe it's not your Hopf algebra, but a quotient of it.
Yeah.
Okay.
Yeah. And so some examples, precise examples. So start with the Zwiddler of algebra. So the base field is assumed to be of characteristic different from 2. The Zwiddler of algebra is just the algebra generated by G and X modulo this relation. So I just use bullet just because this will become the second structure of the Jeter-Drinfeld brace datum. Also for the antipode, I just use D. But okay, it's the same. So what is the Zwiddler of algebra? Is generated by G and X modulo this relation. G square is 1, X square is 0, while X and G anti-commute. And this is a Hopf algebra with coproduct given by this. So G is group-like, while X is Q primitive. So delta of X is X tensor 1 plus G tensor X, while the antipode over G is G and over X is XG. It is known that there is an exhaustive one-parameter family of quasi-triangular structure, which in this case are all co-triangular, given by this. So the quasi-triangular structure on the Zwiddler are classified, and are all of these form here for a scalar parameter, K. And so we are able to use our previous theorem to obtain a Jeter-Drinfeld brace structure and a Jeter-Drinfeld post-Hopf structure. So first, we define a new algebra structure. Precisely, it is generated by G and X modulo this new relation. G square is 1, while X square is no more 0, but it is 1 minus G with scalar parameter K, which is exactly this K here. And X and G in this case commute. Define a new antipode S that fix G and on X is minus XG. And this dot with the same unit, the same coproduct, and the same co-unit, and the new S is an Hopf algebra in the category of Jeter-Drinfeld modules over the starting Zwiddler of algebra. And together, this structure give you a Jeter-Drinfeld brace. Moreover, you are also able to obtain a Jeter-Drinfeld post-Hopf. So just keep the dot structure, so the new structure given with the new antipode S also, and define an action in this way. So G on 1 and G just acts as the identity, while it is substantially minus the identity on X and XG, while X and XG are 0 when they act on 1 and G, while they are these elements when they act on X and XG. And of course, if I tell you that this is a post-Hopf, I also have to tell how the convolution inverse of alpha is made, and it is exactly given by this beta, and this table is exactly this one where you just change sign on this line here. So you just put a -1 for both, and the other is equal. So we can generalize also this example to the of algebras En that are a generalization of the Swidler. So when we start with a field of characteristic different from 2, we can define the of algebra En in this way. We have an element G and nx, so x1 till to xn, with this relation. So G square is 1, xi square is 0 for all x, for all I, xi and g anti-commute, and also xi and xj anti-commute with I and j, different I and j. Again, G is group-like, and on all xi, the delta is skew primitive, so delta of xi is xi tensor 1 plus g tensor xi. T fixes g, and t over xi is xig. And you can see that if we just consider E1, so just one x, we recover exactly the definition of Swidler of algebra. Also for this, we know how the coquadratic structure are made and are precisely given by this. And they are the same of the Swidler, just for this fact here. Instead of having just one parameter k, we have a matrix. In fact, we have parameter which depends on the fact that we have different x. So on xi and xj, we have parameter aij. So this forms a matrix. And if your starting matrix, if this matrix is symmetric, then the structure is cotriangular and vice versa. So cotriangular structure correspond to symmetric matrices bijectively. And again, we can define a new algebra structure generated by this G and then and x with this relation. So as before, G square remain equal to 1, while xi and g commute as before for the Swidler. While for the Swidler, we recall that we have this new relation here, that x square is k1 minus g, and you can read this if you consider xi equals to xj. We have 2xi square. You can cancel the 2 because the characteristic is different from 2, and in fact you recover the relation of that you have for Swidler. But if you consider I different from j, xi xj is minus xj xi plus this other part here. So this new algebra structure with a new S defined in this way that fix again g, while on xi is minus xig, gives you an of algebra in the category of Drinfeld modules over the starting of algebras En. And again, a Drinfeld brace. So define again an action. This also is the same that we have for Swidler. Again, we have an aij since we have xi and xj, while before we have just one x, but it is the same table. And this forms a Drinfeld post-Hopf, where again the convolution inverse beta of alpha is the same table where we change signs on this line here, on the third line. So the last example is the of algebra SLQ2. So if we start with SLQ2, so generated by these 4 elements, A, B, C, D, with the many relations. So these are the form commutativity condition. So where we put, in fact, a scalar Q different from 0, while B and C commute. We also have the quantum determinant condition here. We know that this is an of algebra with comatrix comultiplication, so this must be read in this way. So delta of A is A tensor A plus B tensor C, so just as a product. Epsilon is 1 on A and B, while it is 0 on C and B. And the antipode T interchanges A and B, while it substantially fixed C and B with a scalar. And we know that this is co-quasi-triangular with this structure here. But now in fact, we are able to define a new algebra structure, which is generated by A, B, C, D with this new relation here. So again, we have the form commutativity condition for A and C, just with a scalar, A and B. Now A and D commutes. While this condition for BD and BC and CD are a little bit more strange. In fact, BD is DB plus something in AB, CD is DC plus something in CA, and also for this one. But this is an algebra structure, and with a new S, in fact, is an off-algebra structure over the category of Drinfeld modules over the starting SLQ2. So we start with SLQ2 and we define a new off-algebra structure, which is an off-algebra in the category of Drinfeld modules over the starting SLQ2. And you can see that in this case, again, the antipode over C fix C with the scalar and also over B, while S of D is A as before, while S of A is something in D plus something in A. So this is the definition of the new antipode, and this gives you a Drinfeld brace again. And if you can also define now an action in this way. So you can see that A over everything is substantially the identity. So just for B and C, you put a scalar, Q minus 1 and Q. And the same for D over everything. Just Q and Q minus 1 are in interchange, while C is 0 on everything, while B it acts in a bit different way. So B over B is 0, while over A is just B with this scalar. Over D is B again with this scalar here, while over C is D minus A with this scalar here. And this forms a Drinfeld post-Hopf, where again the convolution of alpha is defined by substantially the same table. You just have to change Q with Q minus 1 in the first and the last line, while in this line is exactly the same of this, just multiply with minus Q. Yeah.
So this table, if I think here of the classical limit, this looks very strange, because like if I simply put Q to be equal to 1, yeah, I see that so A acts as the identity, so does D, and B and C are simply they act as 0, right?
Yeah.
So how should I understand this classically? So why is this happening?
Sorry, why?
I don't understand what this action should be in the classical limit. So does this somehow correspond to some adjoint action, or what is this in the classical limit?
I don't know. No, it should be, in fact, it is just the identity or the 0 action in a sense. I mean, C and B act trivially.
Yeah.
And yeah, but you're right, because the epsilon on yeah. I don't know to what it corresponds in the classical.
Okay.
I don't know.
Anyway.
Okay, and this forms, in fact, a Drinfeld brace. And this was the last example. Then in the last part, I would like to speak about a relative Rota Baxter operator, which is the missing part of the puzzle. So we can define a Rota Baxter operator on Lie algebras and on groups. So the definition of groups is more recent, but we need more the one of Lie algebras. But we will also use this other one. So just what is a relative Rota Baxter operator? When we speak about a relative Rota Baxter operator, we mean of weight 1, just because we consider a starting bracket, so starting braiding. So our vector space, our G is not just a vector space, but it is a Lie algebra. So this means weight 1. So we have this part here. With weight 0, this is just 0, but we need just a relative Rota Baxter operator of weight 1. And this is, so start with an action of a Lie algebra H on a Lie algebra G. So a linear map from G to H is a relative Rota Baxter operator with respect to G, with fixed action, if the bracket of two images, PU and TV, is just given by the image through T of what? of the bracket of U and V plus TU, which acts over V, minus TV acting over U. And clearly, you can give this substantially the same definition for groups. So if you start with an action of a group H on a group G, then just a map from G to H is a relative Rota-Baxter operator on H with respect to G with this action phi if the product of Rg and Rk, where G and K are elements in fact in G, is given by the image through R of this product. So of G dot the action of Rg over K. So these are the definition of Rota-Baxter operator between Lie algebras and between groups. And there is this nice theorem that tells you that you substantially have an adjunction between post-Lie algebras and relative Rota-Baxter operator on Lie algebras, given by Bei, Guo, and Ni. So when you start with a relative Rota-Baxter operator on a Lie algebra H with respect to G, then you can define a post-Lie algebra structure on the domain G, where you just define the new harpoon using the action that you have of H over G. So U harpoon V is just TU acting over V. Vice versa, if you start with the post-Lie algebra, then the identity between your starting Lie algebra G to the subjacent Lie algebra is a relative Rota-Baxter operator. Well, I recall that the subjacent Lie algebra has this new bracket here. So when you start with the post-Lie algebra, the definition was given before, just the identity is a relative Rota-Baxter operator between the subjacent Lie algebra, the starting Lie algebra and the subjacent Lie algebra. So in the paper of Li, Sheng, and Tang, this adjunction is generalized to the case of co-commutative of algebras. So they, in fact, provided an adjunction between co-commutative post-Hopf and relative Rota-Baxter operator on co-commutative of algebras. What we want to do is just to generalize this, removing again the co-commutativity assumption. So we can give this definition. So in the paper, in fact, we give a different definition of also pre-Rota-Baxter operator, something different. Here, I just put the precise definition that we need to build the adjunction. So you start with an of algebra H, and something which is in Drinfeld, in of algebra in Drinfeld modules over H with an action, an arbitrary action denoted by this harpoon, while the coaction is precisely obtained from the adjoint coaction of H using a morphism of coalgebra R. So what we have is in fact this. We have an R which goes from K to H, and H is a standard of algebra, while K is an of algebra in the category of Drinfeld modules over H with this harpoon and this adjoint coaction through R, in a sense. So this R is a Drinfeld relative Rota-Baxter operator if these two conditions are satisfied. So the first one is exactly the one that also Li, Sheng, and Tang gave. So this morphism is not a morphism of algebras, but I can tell you what is the product of two elements, Ra and Rb, is just given by the product of A1 with this action here. You can see that it is exactly the definition that we have for groups. If we come back here, if we come back here, and we consider this as a Hopf algebra, then you just put a 1 here and the 2 here. And it is exactly this definition of Rota-Baxter operator, the natural generalization of a Rota-Baxter operator between groups. But we also need a really strange condition, but we need it, involving the antipode, which is automatically satisfied in the co-commutative case. So if you consider stuff which is co-commutative, this second one is trivially satisfied. I do not know if one can prove that this automatically holds also in this setting using different tricks. This I don't know. But in co-commutative case, you can see that this is automatically satisfied. And so the definition of Li, Sheng, and Tang is exactly what? Is a morphism between two standard co-commutative of algebras, because now this coaction again is trivial if we assume co-commutativity. And so K becomes a standard of algebra. So the definition of Lee-Shengen-Tang is just an R, which is a morphism of coalgebras between two co-commutative Hopf, satisfying just the first one. Just this. This is the... Yeah. This becomes substantially the... it is used to prove the antipode property, in a sense, when you define properly the new antipode and the structure. Yeah, I'm not sure if maybe this can be obtained also in this setting. I'm not properly sure that it is independent. I don't know. Maybe it is needed for sure, but maybe one can prove that just with one and with some tricks, it is automatically satisfied. This I'm not sure that. But okay, you can see that if your starting H is co-commutative, this is trivial. This is, you can change A1 with B2, and that's not A1 with A2 and B1 with B2, and so that's no problem. So in fact, well, we also have the definition of a morphism of Drinfeld Rota Baxter operator, which is clear given by a pair of morphism between the domain and the codomain, satisfying some qualities. And in fact, when your K is co-commutative, then K becomes a standard of algebra, and T2 is automatically satisfied, as I said before. And so one recover the notion of Rota-Baxter operator on co-commutative post-Hopf. I want to point out that in this case, in the paper of Lee-Shengen-Tang, they don't give a definition of Rota-Baxter operator for Hopf algebras, and these two notions coincide under co-commutativity. They give a definition for relative Rota-Baxter operator on co-commutative of algebra. So they just give the definition under the co-commutativity assumption. And again, as it is proved also in the paper of Lee-Shengen-Tang, because again, here we are considering structure which are group-likes and primitive elements, so are co-commutative, so the definition are the same. If we restrict our Drinfeld Rota-Baxter operator of just, in fact, relative Rota-Baxter operator between co-commutative stuff to group-like elements, this is the relative Rota-Baxter operator between groups. And if we restrict it to between primitive elements, this is a Rota-Baxter operator between Lie algebras. So starting with your Rota-Baxter operator between co-commutative of algebras, restrict it to groups. This is a Rota-Baxter operator between groups, and restrict it to primitive elements. This is a Rota-Baxter operator between Lie algebras. And now we are able to give this adjunction between Drinfeld post-Hopf algebras and Drinfeld Rota-Baxter operator that mimic, in fact, the theorem that we saw before, so between Lie algebras. So when you start with the Drinfeld post-Hopf, your Drinfeld Rota-Baxter operator is just given by the identity from H into the subjacent of algebra. I recall you that when we start with a post-Hopf algebra, which is not an Hopf algebra, we are able to define a proper Hopf algebra, the one that we called before subjacent of algebra. And in fact, here we have a standard of algebra, while the H dot, so the starting of datum here, is an Hopf algebra in the category of Drinfeld modules over this one. And in fact, this coincides with this is coherent with the definition of Rota-Baxter operator. So just consider the identity. While if you start with the Rota-Baxter operator, again, you are able to define a Drinfeld post-Hopf algebra on the domain just using the action that you have of H over K. So I recall you that in the definition of, in the definition of relative Drinfeld Rota-Baxter operator, in fact, K is an Hopf algebra in the category of Drinfeld modules over H. So you have an action of H over K. And you just do the image through R. You just do the image through R and then use this action as a new post-Hopf algebra structure on the domain. And you can see that this precisely mimic this theorem here. So when you have a Rota-Baxter operator, you define a post-Lie algebra structure on the domain just using the action that you have of H over G, while if you start with a post-Lie algebra, you just take the identity. between G and the subjacent Lie algebra. It's exactly this adjunction in the setting of algebras. Now, if we assume cocommutativity, again, K becomes a standard of algebras, and we recover exactly the adjunction given between cocommutative post-Hopf and a relative Rota-Baxter operator on cocommutative of algebras given by Li, Sheng, and Tang, just in the case of cocommutative stuff. If you consider now bijective relative Rota-Baxter operator, you have an equivalence with the Drinfeld post-Hopf. So this adjunction here, which is just an adjunction in general, if you consider Rota-Baxter operator which are bijective, becomes an equivalence of categories. In case R is bijective, I also want to point out that R-1 is coincide with the notion of Drinfeld one cocycle that in fact we introduced in the paper of with Davide. So under bijectivity, Rota-Baxter operator are just the inverse of one cocycles. But here the adjunction is given with something which is not bijective in general. Under bijectivity, this becomes an equivalence. And I think that that's all. And so I thank you for your attention.
Do we have questions? Okay, maybe I can start with a very broad question. So we have seen now an equivalence, or like even an isomorphism, as I said, between, so you have matched pairs. You have Drinfeld braces and Drinfeld post-Hopf, right?
Yeah.
So now they are all the same. So what is the benefit of each of them? Why would you say you should look at this and not that?
Yeah, I have to say that let's say the post-Hopf definition comes from the Lie algebra setting, while the brace definition comes from the group, the group setting. So they are the same, but in a sense, they come from different motivations. I have to say that I like the one of Drinfeld post-Hopf. Maybe I can show you for a reason. It is no, it's before. So let's see. So the one, for instance, of Drinfeld post-Hopf, just consider also the classical post-Hopf algebra. So where the definition is just given by a standard Hopf with this harpoon that satisfies 1 and 2 with a convolution inverse. So this definition just tells you that you have an Hopf algebra with something which is not an action, but kind of action in the sense that it is quasi-associative, and it is also multiplicative in this sense. And so this is, in a sense, it is more natural, maybe, while the one of brace is a bit ugly, and you have two of algebra structure with a very strange compatibility condition. But they, in fact, are the same, are isomorphic, but they come from different, you have different motivations, probably. If you look at this, maybe you are, this is more, I don't know, it is more feasible maybe to do something related to Lie algebras using this. It's more natural to look at stuff related coming from Lie algebras, but in fact they are the same. So the information clearly is the same. So they are the same categories essentially. You just rewrite stuff. And with this you can see the connection with the post-Lie algebra world. With Hopf brace you can see the connection with Rota-Baxter on groups and one cocycle over groups. So it is just two ways of see the same thing, but maybe you can do different stuff later. It's more comfortable. I don't know. It's more but it is the same for sure. It's the same as the category is the same. So
and maybe another quick question. So like last year you told me that for the screw braces there is some correspondence with Hopf-Galois extensions, right? And so did you make some progress on figuring out some connection between Hopf-Galois
we are
and, like,
working on this
braces,
with Davide also, and also Sen Rapeniers, which is also another PhD student of Vendramin. But we are not, in this moment, we have not so many results, but we are working on this. There is a deep connection with this, but it is different from the skew brace case. It's more deep. It's not so easy to figure it out how this works in the case of Galois extensions in general. Yeah, because when you consider just the skew brace case, you just consider Galois structures on extension of fields which are also Galois. So you have a lot of information, lots of stuff becomes easier in a sense. Well, the general picture is not clear. There are some generalization of the theorem of Stefanello and Trapeniers for skew braceoids. So when you, also when you don't assume, if I remember well, the extension is finite Galois. So if you remove this condition, you pass from skew braces to skew braceoids. So it's not so easy to pass to the general case of.
Okay, so are you
Galois.
telling me that now there's a whole story of Jetta Drinfeld post-Hopf?
Yeah, probably. Mhm. Yep. Yep.
Formula that goes from the category of Lie algebras to the category of algebras that takes the Lie algebra to its that.
Okay. Mm-hmm. Mm-hmm.
If I want to
Mm-hmm.
I get algebras and everything to the algebra.
Mm-hmm. Yeah. Yeah. Commutator.
There's some way, so you know, the algebra, and then is there some replacement for the category of algebra, some post algebra?
Probably there's something, but I'm not sure. But probably there is something. Yeah, I saw something. Yeah, related to post algebras, but I don't know how they are made. But probably there's something in the literature. Probably, yes.
But back when you had the quantum SL2,
Yeah.
and the focus is random construction, and you use that to build this new.
Yeah. Where it was so.
Yeah.
Is here. Okay.
And so this thing, does this have, I'm thinking in terms of quantum homogeneous spaces, so we think of SL, usual quantum SL2,
Mm-hmm.
classical quantum SL2,
Mm-hmm.
Z algebra grid.
Sorry.
Z algebra grid.
Uh-huh.
We see what part of this is.
Uh-huh. Mm-hmm.
Does this
Oh,
this algebra forms?
I don't know. I never thought about this.
Does that
Mm-hmm. Mm-hmm.
A T about D?
Mm-hmm.
Does that?
I don't know.
Is that maybe now we have a question, maybe that's not an algebra morphism in vector spaces, yeah, maybe it's algebra morphisms in.
Mm-hmm. It's a good question.
Spaces, but now.
That's a nice question. No, but
I mean, this Shannon, she used this algebra all day. I mean, actually, it's probably the construction.
yeah, this in fact is the transmutation of. Yeah, because when the structure comes from a quasi-triangular structure, the dot is the transmutation of the bullet. Coincide exactly with this.
Same with this guy, the problem with the bicovariant calculus of classical dimension is this is being recorded, It's like, oh, no, see, then if you have an analog with Adler calculus, okay, it's more of a common.
That's interesting. That's interesting.
First question is if you ever considered the H-bar deformations of post-Hopf algebras, and if you know if these deformations are governed by some cohomology.
This I don't know. I know that post-Lie algebras can be seen. So for post, I think that for post-Hopf, very less is known till this moment. While for post-Lie, something more is known. And I know that the definition of post-Lie can be seen as a 1-degree order or something bigger. But I don't know how it is extended to higher order. I never look at it, but yeah, I think that something is done in this direction, but I don't know precisely what. So yeah, for post-Hopf for surely it is not known because yeah, they are really new. The paper of post-Hopf is of if I remember well 2024, so it is of 1 year ago. So, but yeah, published on yeah, I think it was put on archive on 2022 and published in 2024, and now a lot of people are working on this stuff. It's like exploding this stuff because yeah.
Are there some questions from the online audience? If yes, you can simply unmute yourself and ask the question. If not, then let's thank the speaker again. Thank you.
Very much.